Good morning. This is Harshul Sagar, entry number 2021 PH10211, and I shall be demonstrating the role of op-amp as a digital to analog converter. So digital and analog circuits, these are terms that are commonly used. So let us see what they mean. Possibly because we have 10 fingers in our hand, we have developed a system of decimal numbers which is based upon 10 and powers of 10. But this is not very efficient for physical systems because physical systems work on two states, conducting and non-conducting. So they have to be represented in the form of two symbols, usually written as 0 and 1. So that means that the digital circuits, they work on binary numbers. Now let us understand what are analog signals and digital signals. So analog signals are basically continuous variations of voltage or current, whereas the digital signals, they take only stepwise values. For example, 0 and 1. Now we will see the conversion of binary to decimal and decimal to binary. So for example, if I've got a number 1010 in binary, so how will we convert it into decimal? Understanding this conversion is important for studying the DAC. So if I've got 1010, it will basically be 1 into 2 cube plus 0 into 2 square plus 1 into 2 to the power 1 plus 0 into 2 to the power 0, that is equal to 10. Coming to op-amp is a very common device in electrical circuits. It has a typical property that V minus V plus, these terminals, the voltages at these terminals, they are equal to each other. And there is a virtual short between these two terminals. This is because the input impedance of the op-amp, Rin, is equal to infinite. So the current entering the op-amp, I1 and I2, they are basically equal to 0. Coming to op-amp as an inverting amplifier, this shall be used in making the summing amplifier that we need for DAC. So for the sake of completeness, I'm explaining it over here. Since we have no current entering the op-amp, we can write the KCL at node A as the following: I1 is equal to I2, and when we solve for V0, this is the value that we are getting. So we can see that it is behaving as an inverting amplifier. Coming to summing amplifier. Summing amplifier, there is only one difference, that we are putting three resistances instead of one resistance. And when we write the equation over here, I is equal to I1 plus I2 plus I3, and solve for it, we shall be getting the weighted sum of the voltages. So it is some constant K into V1, plus some other constant K2 into V2, plus some other constant K3 into V3. So these constants are determined by the ratios of the feedback resistance with R1, R2, and R3. Now I can represent multiple signals in the form of this digital to analog converter. I have used op-amp over here, and I can represent multiple signals over here. So let us see how. So if I look at this DAC, then the switch S0 is connected to VREF. And similarly, the switch S1 and switch S3 are connected to VREF. However, the switch S2 is connected to the ground. So that means, which signal does this correspond to? Since S3 is equal to 1, S1 is equal to 1, S0 is equal to 1, they are connected to VREF. But S2 is equal to 0. So we can say that this corresponds to the signal 1, 0, 1, 1. Now we can write the expression for the output voltage using the formula that we previously derived. Since we know that we can express the input voltages as nothing but the value of B1, B0, B1, B2, B3 into the reference voltage, VREF. So if B3 is 0, then it will be simply 0. But if B3 is 1, then B3 into VRF will be equal to VREF. So this is how we are representing V1, V2, V3 in terms of the index Vi and the reference voltage. And when we take the reference voltage common out of this expression, we will see that V0 has the following expression. V0 is equal to minus RF by R into VREF into this expression. So here, if we notice, it is very clear that why we took the values of resistance in this op-amp as this way, like R, 8R, 4R, 2R, 1R. We choose the resistance in the following manner so that we are able to effectively represent the binary signal into the analog signal output, because we know that binary works on the powers of 2. So let us further elucidate this. If we have got B3, B2, B1, B0 as 0, 1, 0, 1, which is basically 5 in our decimal system, and for simplicity, if we consider RF by R as 0.5 and VREF as 2, then we'll get V out on substitution as minus 0.625. Now, if we change B3, B2, B1, B0 to 1010, now this is 10. So we should expect the double voltage. And indeed, if we substitute, we will see that we are getting 1 plus 0 by 2 plus 1 by 4 plus 0 by 8. So that is minus 1.25. In previous case, we got minus 0.625. So upon doubling the binary output, the analog output is also doubling, and effectively we are able to convert the binary into decimal. And for other voltages, we can see in the following table. We have got the values of binary output, and we can see that we are getting the analog output for each value, and they are equally spaced in interval of 0.125. And since they are equally spaced, we can represent them in the form of a straight line as shown in the following figure, and they are in the following ratio of 1 by 16, 2 by 16, 3 by 16, so until 15 by 16 of VREF. So we are able to effectively represent the digital voltage in terms of the analog output, and our purpose is solved. Now, what are the limitations to this DAC? The limitations are that firstly, the output voltage from the reference voltage source must stay constant even when the output current is changing. Then also, it might be difficult to achieve the exact ratio 1:2:4:8 of the resistances. And for larger DACs, the ratio will extend from 1 to 2 to the power n. So if you have got 12, 2 to the power 12 is 2048. So this wide range of resistances might be difficult to achieve. Also, there is a lack of continuity, lack of resolution. We aren't able to represent every voltage over here, like since the gap of 0.125 is there, so voltages between 1 and 1.25 cannot be represented. So the digital representation of analog voltage can never be exact. Coming to inferences, we have seen that how op-amp can be used as a DAC, but there are multiple applications, and it is very interesting device. It can be used as summer, integrator, differentiator, subtractor, logarithmic amplifier, etc. These are the references from which I've taken information for this project. Thank you so much for watching. I hope you liked it.